And our next speaker is Nir Barzilai. Please give him a warm welcome.
It's after the talk, not before. I'm sorry. Thank you very much. This conference is outstanding. I think I'll demonstrate. I'm going to be the third talk on exceptional longevity, and I'm going to validate most of the time and maybe give you more of the biological insights. But I want to just pick on something that Matt Kaberlein said yesterday, that maybe we're at the tip of the iceberg. Maybe there's much more profound answers that we can tackle about the biology of aging, and he gave kind of an idea from what you can do in lower organisms. But I want to say the following. You know, the treatments that we're talking about now have an impact of extending life in humans, 1, 2, 3 years, or health span in several more years. But remember that our potential as a species, and we can argue about that, but our life expectancy as a species is 115 years. Today, the news in the United States is that life expectancy has dropped to 76, second year in a row. So we're 40 years out of our potential lifespan. And that's why I think to study exceptional longevity is exceptionally important. But before I start, I just want to make one comment. I'm at Albert Einstein College of Medicine, so we're talking about relativity all the time. And this is a double-deck toilet, if you were wondering. And it's always better to be the management than the employees. Morton just showed you how he treats his people. Run faster, right? But I actually want to make the point that we people gave them lots of shit, okay? And let's give our hand today too, tomorrow too, for this organization. It's really exceptional. So, okay, so we have the hallmarks of aging. We really know a lot about them because we have all those longevity models that changes all those hallmarks of aging, and they induce health span and lifespan in animals. But is there something that we can learn from human that slows aging? And this is my family. You had the 6 sisters without the brothers. Those are 4 offspring, 4 siblings that were born in New York between 1910 and 1920. And what's unique about them is they all live to be beyond 102. Okay, 110. Oh, this is not working. Doesn't matter. On the left, it's 110. The little sister was 102, 107, and 109. So, it tells you all the story and kind of gives you another example of this family. They didn't have other children. That's all the children that were born. And to make another point, the sister that stands on the left, that Helen, she lived to be 110. I met her in a New York apartment when she was 100 years old. She opened the door and she was smoking. Okay? Vera, your question. And I asked her, tell me, none of your doctors told you to stop smoking? And she said, all the 4 doctors that told me to stop smoking, they died. Okay? And I'll show you how many are smoking, but the point is that I'll make is that this is in spite of their environment. Now, we have 3,000 people in our studies. Out of them, 750 are centenarians. We have 2 studies where we collect the centenarians, but then a longitudinal study of their offspring, pretty much like Kare introduced, except they're coming to us for, I don't know how it's there, but coming for us every year. And we establish a lot of things from them. We have their cells, we have the immortal cells, we have cell lines, we have omics of everything. But what we have, and we all should have bigger number to get all the secrets, but we are doing it in Ashkenazi Jews only. It's very important in genetic study to try and focus on a genetic background of the population. And per genotype, it's genotype specific, but we need between 20-fold to 50-fold less people in order to get the statistical measurement there. So it's a very powerful tool. It happens also in the United States much more than Denmark. Life expectancy is so much a socio-economical issue because there's no healthcare. You know, United States is, before the announcement today, is 36 in the world for life expectancy. It's just absolutely terrible. But the Ashkenazi Jews are very homogeneous from an education perspective, and that's why they have also healthcare. So we have a homogeneous population that's really telling a lot. And I'll tell you now up front, the data that Kare told you is exactly the same. They have half the mortality, they have half the cardiovascular disease, half the Alzheimer, the offspring. I'm talking about the offspring of centenarians. It's really quite incredible. It's much bigger data than what we are seeing for effects of drugs that we are predicting. Of course, the first question for us is, do they get disease when we all get disease and they just live sick for longer? And the answer here is not. Those are two studies. The left two lines, the black and green, are control, and the red and blue is the centenarians. And this is Tom Pearl's study of centenarians and ours. And you see basically that their health span is increased by 20, 30 years. Okay, everybody's healthy in the beginning. The control get a lot of diseases after the age of 60. Only 10% of them don't have a disease. And the centenarians are just living much healthier. In fact, our centenarians in blue, after the age of 100, 30% don't have a disease. Sometimes they just don't wake up one morning. But this is not the important point. The important point is not only they had health span, but they have a contraction of morbidity. Okay, they're sick very little time at the end of their lives. They live healthy and pretty, squaring of their mortality, but also from a health cost perspective, and you've heard in the last years of the CDC looked at the last two medical costs in the last 2 years of life. And if you die after the age of 100, it's third than if you die at 70. So that's part of the longevity dividend, not the only thing. So I hope I convinced you that it's important to study them. So we had basically one of three hypotheses. We checked three hypotheses. One is, they did what we now all are doing. I see you're here very healthy and you're exercising and you're eating the right thing. Maybe they just done that. Maybe it's all about the environment. Second, maybe they had the perfect genome. What do I call the perfect genome? We know all those SNPs that are associated with cardiovascular disease, Alzheimer's, cancer. Maybe, one of 10,000 people just have the perfect genome. And if not, maybe they have those longevity genes that slows their aging, or they do some protective effect or cause resiliency or something like that. So let me take care of the environment, although Kare said it already, but more than almost half of our people are overweight or obese, still when they're 100 years old. Okay, so it's not that they've been caloric restricted. 60% of men and 30% of women were smoking, heavy smoking or current smoking. Alcohol daily, they don't have that much. Physical activity, and I'm talking about just walking or cycling or housework, less than half of them. Vegetarians, 2%. And it's interesting because we have in the United States the ENHANCE study, which is a study that looked at similar outcomes. That's ENHANCE 1, so it's relevant to their cohort. And they're either worse or the same, okay? So there's nothing much that they've done in their environment. I mean, imagine if Helen wasn't smoking for 95 years, okay? By the way, if you smoke for 95 years, you live long life, okay? but I think they've shown really quite remarkable resiliency. The perfect genome. So I'll give you just one evidence that I think was shocking for us. When we did whole genome sequencing to our first 44 centenarians. So we had all those results, and we had the ClinVar database. At that time, they had 15,000 pathogenic variant. Pathogenic variant means you probably are going to be sick with the disease. By the way, the clean VAR has changes, there's more, they took some of the pathogenic variant out. But this is what we had to work with. And we said, let's just see, maybe they have 0, okay? That'll be a compelling answer. We certainly didn't expect that we have over 230 mutations or SNPs that should have made them ill, okay? And they were not, okay? They were not. And are you asking, if you're asking, are those very important? Yes, the L44P for Parkinson is a very important mutation. We have 2 centenarians who should have been, with ApoE4 genotype, should have been demented at age 70 and dead at 80. They're at 100 and not demented, okay? And it goes all in all, okay? So basically, they don't have a perfect genome. In fact, it looks like they can harbor lots of genes and it doesn't bother them. Their aging is slowed enough. Okay, why is the genetic important? And I think you see in pharmaceuticals, beginning with Regeneron, but everybody else, they want to have a proof of concept from humans. Okay, it was enough that in mice we gave them important pathways and they failed 95% of the time. And I'll give you the two examples, one a general example and one relevant to longevity. The PCSK9, it's a new, very potential treatment that didn't come from the labs. And in 2003, there was a family study that shows that the PCSK9 gain of function caused familial hyperlipidemia. In 2006, they found a loss of function mutations that reduced heart disease by almost 90%. By 2012, they had a phase 3 trial published in New England Journal of Medicine. This is really a very accelerated thing. For aging, we first published in 2006, actually this is where the picture of the centenarians came from in PLOS Biology. We found 14% of the centenarians had SNPs in their ApoC3 promoter, okay? In 2008, Alan Schuldiner and his group showed a different, a null ApoC mutation in AMH that was associated with cardio protection and longevity. In 2014, there were 2 populations with another variant that showed 40% decline in congestive heart failure. And in 2015, there was the phase 3 trial. Okay, so I think genetic is very important. 60% of the drugs that were approved in the last year have been with genetic study or based a lot of genetic study. So pharmaceuticals are looking for the proof of concept. And this is the reference for 2/3 of the patients of 2021 FDA drug approved were from genetic background. I think Joris showed a little bit of the data. What's common in longevity genes, ApoE2 is the most common thing. It always comes. I was very suspicious because, if you have low, if you have ApoE2, okay, maybe you're more likely to come to this study because if you have ApoE4 with dementia, you're not coming to this study. So I thought there could be a ascertainment bias. But in this case, you should have seen also ascertainment bias in ApoE3, and you didn't. So I came very comfortable that this is relevant. FOXO3A was validated a lot. We showed it before. The CETP, one thing I want to say about CETP. CETP, which is a very important cholesterol gene, regulates HDL, kind of a complex system, but it doesn't exist in flies, nematodes, or mice, or rodents, okay? So that's a human-specific gene, and I have to tell you, the most association, the 13% of people who have this mutation, this change, I shouldn't say mutation, but it's a functional change, their cognitive function is the mostly kept. So we have to think that humans are offering us things that we'll never find in animals. I'll talk about the IGF receptor in a second, the growth hormone receptor, and Vera from collaborating in our study have shown 36 mutations, and there's a public company actually in England, right, that is trying to develop drug based on that. So I'll give you 2 points of data here. The first one is, so we have exome sequencing of most of those people, 3,750 centenarians. And we looked, like Jory said before, we looked at rare genotype. We want to see rare things, okay, not the common things. So we look at genotypes that are less than 1%. And what you do supposed to be in the pink that you probably cannot read, but you do the Manhattan plot. You take people without longevity, with longevity, and you see the differences between them. But that's not all you want to do, because we are not based on one SNP at a time. This is something that we did kind of stupidly. We looked at one SNP and said, you have diabetes, you don't have diabetes. But we're not built of one SNP. Okay, and we're built on pathways, and there are up pathways and down the pathways. And so with Zhengdong Zhang, we put the genotypes into a network, okay? And we looked at the significance of the networks. Joyce also talked about a phenotype-based approach. In other words, let's also get data of what we know in aging. This is biasing us already because, as I said, we don't know everything in aging. So what I'm showing you is without that part. But if we just do the pathway approach, what's interesting, up here, those 3 pathways, what we get is what we knew about aging. mTOR, insulin IGF signaling, MAP kinase signaling, and there are other interesting things. Even there's an ovary one, a progesterone one, there's an actin cytoskeleton, but basically for those of you who are doing animals, what we find in animals, we always said that, but it's kind of the difference between longevity in humans and animals. So we are on the right track. It is true that there's many ways to be centenarian. You know, there's not master gene here. And so we need to find all of them and their effects, and we need validation. That's why we need bigger study. Morten, how much time? This was going to be an example of one of the genotypes, just to make the point that, so the genotypes we're getting, like this genotype, is 36 in centenarian and 17 in control. Okay, this is difficult when you have so little subject, or 25 in centenarians and 2 in control. But we can go on, and we're doing it with Yushinsu, who's doing those genotypes in a cell, or Vera and Laura Niederhofer, who are doing the mice models of those things. We can go ahead and do them. But I want to give one example that is really relevant for Morten, most of all, okay? Because we know that the small live longer, right? The small dogs, the ponies, you know, the nematodes. You know, in our centenarians, so they're already centenarians, the women with the lowest IGF-1 live twice as long, okay? There's mortality, they live twice as long. And 60% of the centenarians have some alteration in the growth hormone IGF system. Let me skip that. But I'll give you an example that's really relevant for you so that you don't get upset, okay? We looked at Gilad Smon, comes to me one day, he looked at the deletion of growth hormone receptor that is actually quite, the homozygosity is quite common. You know, there's some of you here with this mutation. And he said, look, when we look at the mutation with age, the centenarians have 2-3 times more of those mutations. I said, okay, what's their IGF-1 level? And he said, well, their IGF-1 level is actually low. And I said, great, what's their height? He said, that's the problem, they're taller. I said, you know, it's 10 years that I sat with the data. I said, I cannot, you know, I cannot sell that, okay? Why are they significantly taller? So he said, what to do? I said, do validation. He said, okay, replication. He did replication of 3 other studies, older Amish, French Caucasian, CHS study. Those who lived longer had significantly more of this growth deletion in exon 3 in growth hormone receptor. With Hassi Cohen, who we collaborate on the IGF for a while, we send them the cells of our centenarians. We have immortalized cells. And he looked at the activation, the phosphorylation of ERK in response to stimulation. And what you see on the left in serum-free, that's the SF. In serum-free, they produce less IGF. They produce less activation, I'm sorry, but that will lead to less IGF. But when growth hormone was high, it was flipped. All of a sudden, this deletion became a very active receptor. It's the same with proliferation. So to make the story short, when those people go through puberty and growth hormone is high, they just grow tall, okay? And when growth hormone goes down, they have low IGF, okay, but they're tall already, and then they live longer. Are you that kind of a guy? So far, so good. Can we do something about that? Well, and this is to Sarah, we in old age, okay, in old rodents, we took IGF receptor antibody that was developed for cancer, okay, and gave it, you give 1 shot a week, a very effective drug, and we start in older animals, and we had a pretty good extension, 9-10% extension of lifespan, but even much more in health span. This is published, but I mean, the cardiac function was twice improved, exercise capacity, sensory motor function. So as you said, it's not too late to target aging, and you can see that from genetics you can go to treatment. People are saying, oh, you're doing genetics, so it's a genetic treatment. No, it's not a genetic treatment. You know the mechanism, you develop drug, right? I just want to announce on behalf of AFAR and Jim Kirkland, who's the president of AFAR, where is he? I just saw him a little bit ago. We started a super ager initiative, and our goal is to recruit 10,000 families of centenarians. Somebody said, I don't know, George said, we should be more diverse, we should have more people, we should have more for replication, validation, so we're actually doing that. So I think you know already that age-related disease can be prevented. You know that people with exceptional longevity have a very important genetic application to slow their aging, that drugs can be developed, and that the super-agers will allow more validation and information. Thank you very much, and good luck with your genetics.
Thank you so much, Nir, and thank you for giving me hope. So that's great. Thank you. Marco has a question.
Marco, your questions are too hard. I'm sorry.
Well, first of all, thanks much for giving me some hope, being so short. At least now I might be, living long. But so if you take these extremely longevous individuals, do you think that they will still benefit from the same interventions that we are developing from the more normal?
Okay, so let me, I believe they might. As I said, I don't know if Helen would live even longer, but I'll tell you an example. With Yushin Su, we discovered that 6 of our centenarians have mutations that are consistent with complex 1 of the mitochondria that is the site of metformin action. Do we want to give them metformin? Wouldn't we maybe block totally the mitochondria and they'll collapse, right? So it's a very good question. I think they're there. The centenarians sometimes ask, what do you have for me? I said, you're that. That's what I want for everyone. But we'll find out eventually. Good question.
Cool. Short question and short answer.
Yeah. Thank you very much for a very informative and always entertaining talk. My remark was on your opening comment that we should study exceptional longevity due to the falling life expectancy in the US. My impression from demographic data is that the reason for falling life expectancy in the US is not lack of exceptionality in the upper end, but very high mortality rates among younger people not related to aging.
Yes, Thank you.
Okay, great. Thank you so much, Nir. And we will have dinner now.